Okay, hello and welcome to my channel. Today, we're going to talk about the spectrum and continuity conditions for a system with potential energy. So, before this, we have only considered free waves and free wave packets, and today we're going to put a potential in the system as well. So let's first start with the stationary states. As you know that it is only dependent on the x part mostly. So let's consider our time independent Schrodinger equation here. So I would write h of psi of x equal to e psi. Okay, and with this you have your Hamiltonian is Hermitian, right? So the eigenstates of your Hamiltonian would form an orthonormal set. So it would look something like this. 1, 2, 3, and so on. Right. These would be assigned to energy. That's 1. So, yep. These. So this is called your spectrum. So basically, it just assigns these eigenfunctions, which are a bunch of stationary states, to an energy. And now we're gonna consider one with potential. So suppose you have a potential, okay? Suppose potential v of x. Okay, it can't look like anything. It can be a hole, a barrier, a spike, or just something like a road that has a hole in it. It can take many forms. But just remember, when you have a potential, it won't be as simple as free waves. And adding a potential would change your time independent Schrodinger equation as follows. So let's write down your time independent Schrodinger equation. That is this, and you would remember this is equal to the energy, right? Now the energy is split into a kinetic part and a potential part. And here, let's say that your potential is greater than your energy. So let's consider your potential to be something like this. Okay, and your energy is somewhere here. So that is less than the potential. So we would have to rewrite this as, well, rewrite this as your v of x minus your e psi. Okay, it can get a little bit confusing here. Why is your potential greater than your energy? That is weird. Okay, but we're gonna talk about that later on when we talk about wells, potential wells and stuff. Okay, and this is the form of Schrodinger equation you would like to use to solve these problems with potential energy, and this would have to obey some conditions that is here. So these conditions is that your wave function, your psi of x, has to be continuous. So it cannot just be something like, well, like this. This is not allowed, because there is a discontinuity here. So that won't be allowed. So that is immediately eliminated. All right. And next is that your psi has to be continuous unless there is one problem that would have discontinuity in your wave function, and that is only if and only if your potential has a delta function. So we're going to talk about the delta function later on, but now it's just a brief introduction to delta functions. So suppose a delta function is just a rectangle with infinite height and infinitesimally small width. So we would kind of draw it as something like this that would spike up to infinity, and this is infinitesimally small with the full area equal to 1. That is the definition of a delta function. Don't get this confused with the other delta like Kronecker delta and Dirac delta. Those are different things. No, Dirac delta is kind of related, but that's besides the point. And next is that if the derivative of your wave function is discontinuous, then the second derivative of your wave function would be proportional to a delta function, and your potential will have a delta function as well. So these are just like some textbook definition, and you will see that clearer when we're dealing with these problems, and they won't be as complicated as now. So I guess that's it for today. Today is just a brief introduction to things when you have to deal with energy with potential. Alright, and I guess that's it for today. Goodbye.